My name is Alan Jeary and I'm a structural engineer. My background has included doing research in the United Kingdom in electronics first and then structural engineering. I moved from there to Hong Kong where I was a chair professor teaching building construction, and then I moved from there to Sydney, Australia, where I also did structural engineering and was the head of department of a department doing structural engineering and fire engineering as well. And then I moved to the United States and became a partner in a company doing structural integrity assessments.
My name is Alberto Ortigao, and I did my degrees in Rio de Janeiro in Brazil. After post-graduating, I became, soon after, assistant professor and then professor of geotechnical engineering at the University of Rio. And I had the opportunity to travel and work overseas for a few years. I worked in Britain, was my first international experience, then Canada at the University of British Columbia, later on in Hong Kong with Dr. Jeary, and later on also in Australia with Dr. Jeary as well. So I have 50 years, over 50 years of geotechnical experience. During all these years, I have monitored too many structures, from dams, embankments, foundations, whatever.
I should say that not only did Berto come to work with me in my department, I came to work with Berto in his company as well. And
Yes.
Together we've performed a whole series of tests together as well.
I think one of the most challenging type of work to have today in geotechnics are the dams, especially the tailings dams, in which we have seen a lot of disasters in the last years. Also tunneling. Tunneling is a very risky work in which we always see problems, we see disasters, we see failures. And so these two structures are the main structures that have a high risk, and they should be monitored, all of them.
The biggest challenge at the moment in structural engineering is that structures are failing all over the world, both with bridges and with tall buildings. Just over a year ago, there was a collapse of a building in Florida, the Champlain Tower. There's been another one just recently in Ohio. There have been collapses of bridges all over the world for various different reasons. So the biggest challenge is, how do you actually monitor what's going on in these structures and try to identify whether they are on the point of collapsing? Because if you can actually sort that out, there's a big market for that sort of thing. People really want to know whether the structure that they're using or living in is about to fall down, not unreasonably.
Well, when I started doing monitoring, everything was done by hand. We had to go there, take measurements, write down the results, then take to a computer, or initially it was only on paper. So it took hours or days for any results to come to the consultant to be analyzed. So this changed a lot. Today, automation is possible. It's not as expensive as it was in the past, and most of these, most of dams and also tunnel structures are being monitored automatically. So that had been a big change in those years, enormous change.
To me, the biggest thing that's happened is the digital revolution. As Dr. Ortigao says, in the early days, we did things by hand. We used analog machines to measure what was going on. But as soon as we put things into digital form, we found that there were so many more things we could do as well. First of all, we could increase the signal to noise ratio, the signal being the thing that you're really interested in, and the noise being what happens in nature, in electronic circuits. And the second thing is that the analysis was so much more impressive. The computing power that you can use now is so much greater, even than 20 years ago. So we can do all sorts of things which we couldn't do just recently.
Well, I think it's automation, but now we are being led to another problem. I have, for instance, a client which I'm talking to. They have 2,000 instruments automated, and they don't have enough people to analyze all this. And we are starting a research project with them to use artificial intelligence, AI, to be able to find out what's going on, because humans cannot analyze quickly 2,000 results from 2,000 instruments.
The ability to be able to find out exactly, as Beato says, what is the particular problem, and the analysis which goes on, which we've been working on for a long time now, has become so much more sophisticated, and we're now working on a new generation of equipment which will give you these answers very, very quickly.
In geotechnical engineering, in general, all process in tunnels, in dams, most of the process, not all, are slow. So we can see the problem approaching. If you have inclinometers, you have piezometers, you may see what's going on. However, there is a particular problem which I'm very much concerned with, is liquefaction, especially static liquefaction. Liquefaction takes place abruptly, and from what we saw in Brumadinho Dam that failed, also Samarco Dam that failed, and perhaps others, these processes were very abruptly, and normal instrumentation like inclinometers and piezometers didn't show any sign of the approaching failure. So the new technology, which Alan is talking about, to measure vibrations and to look at what may the difference in the changing vibration behavior of the dam before it takes place, a failure like that may be a solution.
In Florida, as I mentioned before, there was a collapse of the Champlain Tower, and the authorities in Florida came to us and said, could you have predicted that this building was on the verge of collapse before it actually happened? And we had a one-word answer: yes, we could have. All it needs is good data and the sort of analysis that we do to identify exactly where and how important the problem is.
Well, for instance, in normal instrumentation, a dangerous situation is given by a sudden increase in one particular measure. For instance, if you have a sudden increase of a displacement of a pore pressure measurement, this sudden increase, in many cases, is an indication of the proximity of a collapse situation. So we have to take care. On the other hand, in structural engineering,
in structural engineering, we actually measure the vibrations of structures, and it's rather like taking a measurement off an electrocardiogram of a person. You're looking for things which are changing. We measure two parameters, basically: the natural frequency of the sway of a structure and the energy dissipation in a structure. Then we look at where those things are coming from. So we need good data to be able to find out where it's happening, but measuring the frequency and the damping, which is energy dissipation, very precisely. It's not that simple to do, but we do it, and we look at the nonlinear characteristics of these two parameters, and that'll tell us all sorts of things about the structure. Our analysis depends on being able to get sufficient data of sufficient precision with a very low noise ratio, and that will then allow us to do the sort of analysis that we do to be able to identify what and where a problem is. The risk ratio is essentially comparing the performance of a structure at the time that you're measuring with what's expected in the codes of practice. And the codes of practice actually give you a good identification of what frequency and damping ought to be. When you compare what you actually measure with those, then you'll have a ratio of what's going on with what's expected. Once you've got that, then you've got the risk ratio. You can actually then apply statistics to the risk ratio measurement, and you will identify what the probability of exceeding the acceptable range of performance actually is, how often it'll happen on average. No, we can't. The problem is that there are accelerometers in smartphones, but they aren't sensitive enough. The ones that we actually use are the most sensitive ones in the world. We're building a new generation which will be the most sensitive. able to measure to better than the wavelength of visible light. And that may sound a bit esoteric, but in practice, once we get down into those very low levels, then we can identify all sorts of things which are actually happening in the structure. Yes, it is. In fact, our new generation, which is going to be cheap, can be used by a person inside a building or an owner of a bridge to identify what the risk ratio is and whether the frequency and the damping are changing with time going by. And this is just left in a structure to measure the ambient movement created by small winds, traffic going past, people walking. So there's always an excitation at a low level, but nevertheless, it will be a near real-time assessment of what the risk is and whether it's changing as well. So if an alarm goes off, it's a good idea to evacuate the building.
Well, I think Ackcio technology is very interesting because now we have a very reliable way of automation, and they did it with the mesh technology in which one sensor sent to the other sensors. So the signal could travel, and if there is a problem in one of the signal, it finds automatically a new way, and it's very reliable. And the other thing that Ackcio offers are the tilt meters. The tilt meters measure rotation of a structure, and this is a very interesting and relatively new device which replaces what we did before in the past, which was surveying, which led to human errors. And a tilt meter never makes mistakes, gives always the right answer. So this technology has been very useful. We have been using this on dams, on buildings. It's very interesting.
And as far as structural engineering is concerned, I believe, talking to Berto, that our next generation would be an ideal candidate for use by Ackcio with their approach. And it does sound like an interesting development.
Yeah. Well, I have instrumented in the last 4 years a big dam in which the surface displacement devices were replaced, not replaced, but we had an addition of tilt meters close to them in order to reduce the amount of manual readings. And we had about 40 tilt meters on the slope of this dam, and this has led to a much better solution for a monitoring solution for this project, rather than the old system of surveying. We have now a project in which we are monitoring some buildings close to a wall, and this wall shows signs of movement, and we designed a solution to do ground improvement at the back of the wall, and this is now underway, and the tilt meters are in place. We are monitoring these buildings behind this wall. So at least these two projects show the importance of Ackcio technology for this type of application. We also have designed a lot of tilt meters for tunnels, internal. They are placed on the line of the tunnels, and also this very interesting way of monitoring tunneling behavior.
We are looking at the whole subject area of being able to monitor structures, especially where forensics is concerned. Whether, for instance, you can take a very large load across a bridge without creating a problem. And additionally, just being able to do a baseline of a structure to tell exactly how, in the same way as you commission equipment inside a building, whether the structure itself is actually in a fit condition to be used.
They provide a data transmission solution which is much more reliable than other technologies. I don't know the details because this is all about electronics and that's not my area. What I can say is that their system works very well and is very reliable. It can transmit data to a big distance, so that's why we selected Ackcio systems for our applications. Well, I think most structures, these risky structures, they have to be monitored. Okay, there's no solution without a monitoring system. And when we automate a reasonable number of instruments, if you make an analysis with the investments that you make for the automation, say compared to manual readings, they pay back very soon. In a couple of years, or maximum 5 years, these investments are paid back. And for the structural safety itself, it's a must. It's unthinkable of building a dam or building a tunnel without proper monitoring.
The law has changed in the United States just recently, and that is that they have made in Florida a law requiring that structural integrity is assessed for a building. By the end of 2024, it will be a requirement that there is a measurement of buildings. Now, imagine that all of the buildings in Florida, and there are 10 states in the United States that have followed suit, and then all of the rest of the world requires that this technology is used on all of the buildings in the world. Now, would you like to invest in something like that? I certainly would.
Well, in terms of geotechnical engineering, I think we already have the automation system. What's going to change, in my view, in the future? We're going to have much more artificial intelligent applications in order to check the data quality, to issue alarms, and to issue alarms which are more reliable. Also, we are going to have an enormous development in numerical modeling, which can, in the future, maybe we have an analysis which coupled with the measurements, like a back analysis. And this is going to improve a lot the understanding of the behavior of the structure and make it more safe, make it safer, because it's going to issue alarms in a reliable way.
Absolutely right. I absolutely agree with that. And the issue here is that people talk about digital twins of a structure. So they've created a digital model which they expect to be able to use for predicting things that happen in a structure. But there are all sorts of things that go wrong with these sort of digital twins. What you need to do is to calibrate them, and you do that against a model of a structure, representation, measurements of the structure. You calibrate the digital twin, and that way you have the sort of confidence that Berto is talking about in identifying what creates the alarms. And so you need a high degree of confidence in the alarms going off. If alarms go off and you can't tell whether they're right or wrong, soon the system gets destroyed. But if they're reliable, then they will revolutionize how we go about relying on structural integrity.